Okay. So I'll just start that again. I'm Mark Johnston, FreeBSD developer. I'm here to talk about Numa, and specifically Numa as it pertains to FreeBSD. And even more specifically, I want to talk about a project that was undertaken by Jeff Roberson late last year and early this year to improve the state of things in FreeBSD with respect to Numa systems, and also with respect to scalability of the memory management code in FreeBSD, as well as the buffer cache. Those issues aren't specifically tied to Numa, but they are certainly exacerbated by Numa architectures. So they were all kind of addressed in one fell swoop. I mean, not completely, but a lot of progress was made. So what I'm going to do, or the rough structure of my talk is just going to be to first give an overview of Numa architectures, what they look like, what motivates them. I want to talk a little bit about what they mean for operating systems, the implications of that kind of architecture, and what it takes in order to exploit the performance that it enables. I'm going to talk a little bit about the history of Numa awareness in FreeBSD. Jeff's work represents a pretty big advancement over what was there previously, but it didn't build on nothing. There's been various sort of bits of progress in terms of Numa awareness in FreeBSD for a long time. After that, I'm going to talk about the project itself. The nature of the project means that it wasn't this kind of single cohesive thing. It was actually just a bunch of mostly independent chunks that went into head, as they were ready. So as I mentioned, Jeff did the lion's share of that work. I helped review a little bit of it. I contributed a few pieces to the VM scalability effort. A few other people, Alan Cox, Konstantin Belousov, and Drew Gallatin, spent a lot of time reviewing, contributing patches of their own. So as Jeff isn't here, obviously he's the most qualified to talk about this, but hopefully I'll be a good enough stand-in. So I think I have an hour and a half booked for this. I don't intend to speak for that long, rest assured. I'm hoping at the end there's going to be a bit of an opportunity for anyone in the audience who's making use of the new Numa work to talk about their experience in doing so, talk about what that's meant from a performance perspective for them, and also to talk about any shortcomings that they might have encountered. So Numa, what is that? It's an acronym. It stands for Non-Uniform Memory Access, or Non-Uniform Memory Architecture. And so to motivate it, we take a few steps back. It's long been the case that single core performance has been pretty stagnant in terms of improvements year over year. There's certain sort of fundamental limitations to how fast an economical processor can work. So a long time ago, system designers started adopting so-called multiprocessing systems, where you stick a bunch of CPUs into a single computer system. They all execute code in parallel. It turns out that if you want to write code for such a system, it's extremely useful if all of those cores share a unified view of the system's RAM. So that's the so-called shared memory architecture, shared memory multiprocessing. So it's the case that modern CPUs, however, can issue memory references much more quickly than a DRAM controller can actually process them. DRAM has various limitations that mean that memory references emitted by a modern CPU can take hundreds of cycles to actually complete. So obviously, in order to exploit the performance of processors, we need to do better than that. That's led to the so-called cache hierarchy, where in between CPUs and the memory controller, you have small pieces of low latency RAM, which cache or absorb most of the memory references emitted by CPUs. So some of those caches are CPU local, in the sense that each CPU has its own cache. And then lower in the hierarchy, caches are shared among multiple CPUs. So what they do is they absorb a lot of they hide a lot of the latency to the main DRAM controller. And so they to some extent, hide the problem of slow DRAM. Of course, caches can't absorb all of the memory references emitted by a CPU. So once you put enough CPUs into a system, the DRAM controller again becomes a bottleneck. It's got a fixed bandwidth. If you have enough CPUs issuing memory references, you can exceed that bandwidth, and then the CPUs are starved, and adding more CPUs to the system doesn't help you. So there's a few different ways to solve that from a computer architecture perspective. There's various things like multi-channel memory, which help help improve things. But ultimately, what one ends up seeing is so-called Numa systems, where you have a system with multiple CPUs. They're partitioned into groups. Each group has a local DRAM controller and some local DRAM. When a CPU emits a memory reference, it may go to the local controller and be satisfied there, in which case things look the same as they did before. But if the RAM that they're trying to access is not local, then it has to make an extra trip to a remote DRAM controller where it is satisfied, and then completion is signaled to the originating processor. So the cost of that extra hop to the remote controller is non-zero, of course, and it's the so-called Numa factor, basically the increased latency between, the potentially increased latency between a CPU and RAM. So we have this kind of non-uniform latency. A CPU can access local memory and it completes in a certain amount of time. If it has to go to remote memory, it takes longer. So Numa systems aren't new by any means. There's, in reading literature about them, you can find examples of Numa systems going back to the 90s and 80s. Computer systems are multiprocessing systems that people want to actually program for end up being cache coherent, which basically means that when one CPU updates a block of memory and another CPU tries to access that memory, it sees the updated copy eventually. So the necessity for cache coherency, or the desire for cache coherency, itself imposes a constraint on the number of CPUs in a system. Maintaining cache coherence is inherently difficult to scale. So in practice, Numa systems that one encounters in a commercial setting today are still constrained by certain scalability concerns. So in making FreeBSD work well in such systems, we can make a few assumptions, because Numa systems that one encounters share a few fairly strong traits, and then we can optimize for those traits. So some of them look like, well, I already mentioned that CPU caches are coherent, so that itself is a constraint. In practice, the number of different Numa domains, the number of memory controllers in a system is fairly small. In practice, it's usually 2 or 4. Sometimes one sees systems with 8. But that's pretty much the upper bound. And I think in FreeBSD, there's basically a compile time constant which determines the maximum number of Numa domains that a system can support, and I believe it's 8 on AMD 64 right now. One other common aspect to common Numa systems is that the extra latency that one incurs by accessing a remote RAM is actually not that big relative to the initial cost of a local memory access. It's sort of in the neighborhood of 20 to 50% extra latency. In reading about massive Numa systems, bespoke massive Numa systems of years gone by, you can see factors of up to 10 or even higher. But in general, people aren't really running FreeBSD on those systems. We generally don't need to worry about them. My last point, which I crossed out, tellingly, is that Numa domains are balanced. What I mean by that is that each DRAM controller in a system has roughly the same amount of memory behind it, which is, on the face of it, a fairly reasonable assumption. Most systems are built that way. It turns out that's not really true, and one does have to account for that in the design of a Numa-aware operating system. And that can be for as silly a reason as, one DIMM has failed, and now suddenly you have a system with 2 Numa domains, but one has slightly less memory than the other. There's kind of weird one-off cases. I think Drew Gallatin was the one who wrote a patch for FreeBSD to get it to work on one of the Threadripper 2 variants, which effectively has 4 Numa domains, but only 2 memory controllers. So from the perspective of the operating system, you have you're partitioning the system CPU into 4 groups, but 2 of those groups have no local memory associated with them. So there's 4 Numa domains, but 2 of them are effectively empty. So that's something we had to deal with.
Excuse me, question?
Yep.
So you just mentioned Threadripper having empty domains. On Skylake, Ivy Bridge, Sandy Bridge, Broadwell, Haswell, they have integrated memory controller, and some of them with high core counts actually had multiple memory controllers within the same CPU chip, and then you might have multiple of those in multiple sockets. So Do each of those on-die memory controllers count as their own domain? Or is it
Yes.
Yes.
Turn it on.
okay.
So this is so-called cluster on die, right?
Depends on which lie you want your bias to tell you.
Yeah.
Okay, fair enough.
And the follow-on question is, when you turn it on, it's sometimes measurable,
Okay,
right? So it's not always a lie.
fair enough.
We can talk about the lie.
Oh, yeah. No,
The
no.
lies in you.
The fact that the BIOS lies to you is not the question.
It's a more ambitious lie than other lies. Sorry.
No. And just as an aside, if anyone has any questions or wants me to define anything or try to explain anything, feel free to interrupt me and I'll answer your question to the best of my ability. I'm not an expert on the architecture of Numa systems in general. I've mostly encountered them through the lens of FreeBSD and through that sort of software layer. Yeah, please feel free to interrupt me. So what Numa systems effectively do is they introduce a new layer in the memory hierarchy. And as with all layers in that hierarchy, in order to exploit the full performance of the system, the software that runs on it needs to be aware of it to some degree. Hardware designers can't really hide everything. And in the case of Numa, we have this extra latency. And we also have the desire to try and balance the use of bandwidth across memory controllers. So, I mean, multiple memory controllers are used because there's a certain fixed limit to the number of memory requests that they can handle. If your operating system allocates memory in such a way that all CPUs are going to the same DRAM controller, well, you've effectively just reintroduced that bottleneck. So the Numa architecture isn't really helping you there. So an operating system needs to do things basically to try and ensure that memory accesses, whenever possible, go to a local domain, but at the same time also balance memory controller usage, balance CPU cluster interconnect usage, because whenever you go to a remote memory controller, now you're going over this remote interconnect that has its own bandwidth and is subject to becoming a bottleneck. Some applications know a lot about how they're going to use memory, and so they can do better than the operating system. In general, though, operating systems will use heuristics to try and do something at least do something sane for memory allocations for applications which don't declare any intent to use memory in a specific way. So a Numa allocation policy it usually takes the form of, a Numa allocation policy is basically an algorithm which runs when a memory allocation is attempted by the kernel itself or by a userland application, and it basically just selects a domain from which to allocate a page to satisfy the allocation request. So an example of an allocation policy is just round robin across all of the domains. So you maintain some sort of iterator, just an integer. Every time you attempt an allocation, you increase the value of the integer and use that to select a domain. So I mod the number of domains is your domain index. So in some cases, however, the kernel allocates memory for itself, and it knows a lot about how that memory is going to be accessed. Classic example is per CPU data structures. Those are data structures that are sharded across all of the CPUs in the system. A CPU is only going to ever access the memory or the component of the data structure that's local to that CPU. So it pretty much always makes sense to try and allocate from a local domain for that piece of the per CPU data structure. Another example is DMA memory. Peripheral devices, which access memory, which is pretty much all of them, are also local to a specific memory controller. They do lots of streaming reads and writes of memory. You generally want to set things up so that memory used for DMA operations is local to the device that's using that memory. We also have situations where certain memory domains end up being depleted faster than others for various reasons. We want to make sure that we handle those kinds of cases sanely, in the sense of falling back to a different domain if the preferred domain can't satisfy an allocation request. So there's quite a few different things that the memory management component of the operating system needs to do, or at least that we want it to do in order to exploit the system. So what does that look like for FreeBSD? Well, there's a whole bunch of different subsystems that end up knowing something about the Numa topology of the system. So the CPU scheduler is an obvious example. It knows about the entire memory hierarchy. It tries pretty hard to ensure that once a thread has been scheduled on the CPUs in a specific Numa domain, it doesn't migrate to another domain unless it's really necessary. And so any of the Numa allocations or any of the memory allocations performed by that thread are kind of kept in the same context as the CPUs on which it's scheduled. I mentioned earlier that Userland applications which want to provide hints to the operating system need an interface to do so. For the Numa work, Jeff basically extended the CPU set system call interface. CPU set is a family of system calls that basically let you define subsets of the system CPUs and ask that threads or processes or even all the processes in a jail get executed only on the CPUs in that set. So to that, he added this notion of a domain allocation policy, which can be attached to a CPU set. So when a thread is running under a specific CPU set, it inherits the Numa allocation policy associated with that set. And so that lets you do things like run make build world under a specific Numa domain with a specific domain allocation policy. So bus DMA, as I mentioned, DMA memory allocations have certain requirements, not hard requirements, but there's certain things we want to do. So bus DMA, which is the subsystem in FreeBSD that's responsible for managing DMA memory, has to know about the Numa domains associated with a given device. Aside from that, the kernel itself contains lots of memory allocators, UMA, malloc, the KMEM API, the kernel stack allocator. We want to embed a notion of some Numa domain selection policy in each of those. From the perspective of SMP scalability in general, FreeBSD's had a bunch of bottlenecks in the VM subsystem, especially around the page allocator. So before Jeff's work, we had the physical memory allocator, which managed all the system's free physical pages. Anytime you wanted to go and allocate one, you had to take this global lock, pick a page out, unlock. Obviously that becomes a huge bottleneck once you have enough threads that are attempting to do allocations. We have a few other kind of global data structures in the VM subsystem. There's page queues, which are used to implement LRU for page reclamation. For a long time, those have actually been per domain page queues, but there's still a lot of kind of nasty bottlenecks in there, in the sense that anytime you want to enqueue a page into a page queue, immediately following an allocation, anytime you want to remove a page from a page queue because you're about to free it, you have to take this lock, and in practice, that lock ends up being heavily contended. And there's also the buffer cache used by UFS, which had its own kind of bottlenecks similar to the ones I already talked about. So, like I said, Jeff's work didn't start from scratch. There's been, for a long time, some notion of Numa awareness in FreeBSD. So since 2010, we've been able to parse SRAT, which is an ACPI table that basically encodes the Numa topology of the system. It basically lets you assign a numeric domain ID to ranges of physical memory, and those ranges of physical memory are local to the Numa domain to which they're identified. So since 2010, we've been able to at least embed that knowledge in the kernel. The physical memory allocator has reflected that structure since then. So like I said, the physical memory allocator manages all the system's free pages. And since those commits went in, they basically maintain separate lists, or sets of lists of free pages per domain. So at that point, you could say to the physical memory allocator, which is, again, the lowest level memory allocator in FreeBSD, you could say, oh, hey, I want to take a page from a specific domain, and it would do so, or tell you that there's none left. Along with those two commits came the beginnings of a Numa allocation policy. I didn't look too closely at the details of those commits, but it seemed that the two that I referenced up there introduced a first touch policy, where basically anytime you go to allocate a page, the system would say, okay, well, what CPU is the thread running on? Which Numa domain does that CPU belong to? Okay, we'll allocate a page from that domain. And whether that makes sense as a default policy is kind of debatable, because you can think about situations where lots of processes are going to share the same memory. consider the text section of like libc.so, which is the dynamic C library that's linked into pretty much every userland process. The first application to fault on libc will run its own domain selection policy on the page that it faulted on, but every other application that accesses that page won't be performing an allocation. It'll just use whatever allocation has already been performed. So only the first thread to actually allocate memory for libc will actually have its Numa domain applied. So in that kind of scenario, first touch doesn't necessarily do everything that you want. Because again, something might load 10 pages in libc and they're all on domain 1. Every process that runs on a different domain is now going to be performing remote memory fetches. And there was a commit somewhat later, which effectively changed the default policy to round robin, although it was kind of obscured. In 2013 also, FreeBSD switched from having global page queues to per domain page queues, which helped somewhat with the page queue lock contention that I described earlier. In 2014, we had this branch called Projects Numa, which was done by Jeff and Attilio. And it was kind of, it was this project branch. A bunch of work went into it relatively quickly. It defined this kind of abstract Numa allocation policy structure. It plumbed the notion of a Numa domain through various KPIs, various memory allocators specifically. So all this work kind of went in a few months, and then nothing really happened with it. It was never merged ahead as far as I know. It did serve as the basis for Jeff's later work, but it was just this kind of thing sitting there. So what ended up happening in 2015 is Adrian Chad did some work to basically expose a userland interface for requesting a Numa domain policy. And so along with that work came Numa control, which is just a userland utility modeled after a Linux utility of the same name, which let you specify, I don't remember exactly what policies it let you do, but it for instance, let you run a specific process under a round robin policy, for instance. So that I can't, like, I don't think that was ever actually enabled in generic. So I'm not sure how many users it ended up having. I think one of the shortcomings of that work is while it certainly presented that interface for userland applications, it didn't really plumb domain awareness through various other allocation paths in the kernel. So it was kind of, it was a bit stilted, I guess. But in any case, that was the state of things for a couple of years until Jeff's work, which started in 2017. So it's done by Jeff, sponsored by a few different companies. I'm not sure if IX Systems might also be on that list. I didn't double check. As far as I know, Limelight, Netflix, and Isilon all sponsored him to do this work. What did it actually look like? A lot of it, if you look at the diffs, just really involves adding an in-domain parameter to various layers. In a lot of cases, it just gets passed through. But doing the work of that doing the actual plumbing in a lot of cases takes care and resulted in some fairly large diffs. It defined a Numa allocation policy abstraction, which I'll go into detail in the next couple of slides. It provided an alternate userland interface for requesting Numa domain policies through CPU set. And as part of all of that work, it addressed a few of the bottlenecks that I talked about earlier, the global free page lock and so on. So domain set 9 is the sort of abstract encapsulation of a Numa domain selection policy. So it's just a struct domain set. It's in domainset.h. It's immutable, which is important because it's actually a fairly large struct. Well, it's a somewhat large struct, but the point is, while it's logically coupled to some state, it's the state and the actual policy are separated. I believe that's just to avoid the bloat of combining them together. So the state that one usually has is just an integer. Like I said, for a round robin allocation policy, you end up just incrementing an integer. So the iterator, the state, is embedded in a bunch of key structs in the kernel, struct thread and VM object for now, and probably more to come. And they contain a pointer to the domain set, which defines the policy. So there's an API which effectively, or a KPI rather, which effectively combines the two. You use the VM domain set API, KPI, to run an iterator on a domain set. So the domain set lets you do various things. You can, instead of requesting allocations from, in the round robin case, instead of requesting allocations from across the whole set of Numa domains, you can restrict to a subset of them. There's a bunch of predefined policies available. The ones that I listed here aren't actually committed yet, but they will be soon. We now have this kind of machinery for requesting specific allocation policies. The specific policies that domain set currently implements, there's 4 of them. Round robin I already talked about. It's conceptually quite simple. You just increment your iterator and take the result mob, the number of domains in your domain set. And so successive allocations just look like the example I gave you there. First touch I also already mentioned. You just take the domain currently associated with the CPU on which you're currently running. There's a prefer policy where you request that allocations come from a specific domain, falling back to a round robin policy if the preferred domain is depleted. There's also an interleave policy, which is a bit more esoteric. It's conceptually pretty similar to round robin, but it lets you effectively define a stride in the output. So instead of having, in the round robin case, 0, 1, 0, 1, you can actually request for specific, or for consecutive pages in a mapping, you can request that blocks of them come from the same domain. And then at a higher level, it's a round robin policy. And so the main motivation for that is to help preserve super pages. So with the super page, you basically have this large virtual range. In order to map it using a single TLB entry, you can set things up so that the physical memory backing that virtual range is all contiguous. But to do that, you need to make sure that they all come from the same domain. So if for successive pages in a virtual mapping, you pick alternating domains, then you can't promote that mapping to a super page. So the interleave policy is just a way around that. So there's a whole bunch of code fragments that look like this in the kernel now. And this is basically how you apply a domain set to an iterator. You initialize a structure, DI, which is on the stack, which just contains some state. You pass in the object on behalf of which you're allocating. The object itself contains an iterator and may optionally specify a policy. The current thread also the current thread always specifies a policy. So the object policy is preferred, and the thread policy is used if the object doesn't specify one. So you pass in a bunch of parameters. In particular, you pass a domain pointer, and out of this initial call, you get a domain to try. And then you go into the physical memory allocator and you say, okay, give me a page from this domain, please. If that works, great, we're done. Otherwise, you continue running the iterator. And in practice, that usually ends up looking like a round robin pattern, because that's just the only really sane thing to do in that case. So like I said, if you're doing a first touch policy, we'll try to allocate from the local domain. If that's not possible, we'll just go round robin. So what does the Userland interface to all of this look like? It's an extension of CPU set, the system call interface, which is wrapped by the CPU set command line program. As with CPU sets themselves, we have this notion of a domain set that you can apply to a specific thread, process, or jail, which are the entities that can be manipulated by the CPU set command line program. So you can do cute things like run make build world with a round robin policy alternating between domains 0 and 2. You can ask the system to tell you which Numa domain allocation policy is being used for a given entity, for CPU set 0, for instance. There's a couple of system calls which back this, or which provide this interface. Userland domains, or Userland threads rather, default to a first touch allocation policy, although we'll kind of override that in order to avoid, in order to preserve the possibility of super page promotion like I discussed earlier. And in the kernel, for kernel allocations, we use the interleave policy to provide that same guarantee, that same effort. So in addition to the page allocator, we have a lot of random memory allocators scattered throughout the kernel. These have different considerations than the page allocator. In a lot of cases, when you're allocating a page on behalf of, a process, that allocation is going to be private to the process. But for memory allocators used in the kernel, like UMA and malloc, which just sits on top of UMA, allocations are done once. The result is used and returned to the allocator, but then that result is cached and might be reused again and again. So it doesn't necessarily make sense to use the Numa domain selection policy of the first thread that actually allocated the page, because we can't really say much about how the object that's actually returned by UMA is going to be used in the future. So what we do there is we actually just hard code a round robin policy, try to balance things out. And then there are more specialized KPIs, which malloc domain, which just uses, or which preferentially attempts to allocate from the specified domain. So if you're setting up per CPU data structures and so on, you can still ask for specific domains. KMM malloc, which is just another kernel memory allocator, also uses a round robin policy and also plays a few games in order to preserve the possibility for super page promotion. BusDMA, like I said, we try to allocate memory that's local to the device that's actually going to use the memory. So there's a bunch of plumbing that was done there. Under the cover, it uses malloc domain to actually do those allocations. So the page allocator is what you hit anytime you take a page fault on a virtual mapping. Much of the time, allocations that are performed this way are going to be private to the application, but that's not always true. And I gave the example of libc.so. So when you take a fault, the object to which that page is going to belong can specify a policy. If not, the thread will do that. At the moment, there's no interface for actually assigning a policy to a given VM object. So that's kind of a limitation of the current mechanism, but there's no reason we can't have a system call akin to Linux's mbind, where you basically specify a virtual range in your process, and you say, I want to associate that, or I want to use a specific Numa policy to satisfy allocations in that range. So the fact that we have this domain set iterator embedded in a VM object permits the construction of such interfaces. And you can also, there's a VM object associated with each vnode. You could play games like, for all allocations for pages for a specific file, use this policy or a specific file system and so on. So there's a lot of the machinery that we can, there's a lot of machinery that we can use to make fine-grained decisions about Numa policies. And as always, when the caller knows more than the operating system, we have specialized KPIs that let you specify a specific domain. There's also the kernel stack allocator, which has come up recently as a result of a couple of regressions. For kernel stack pages, we currently use a round robin policy, which is probably not optimal. There's certain cases where you have kernel threads which are always going to be performing operations specific to a domain, like iThreads for a specific device, for instance. Kernel stacks are cached also, so the selection, or so the domain selection performed when you initially allocate a stack is going to carry over if that stack is cached. So there's some work to do there, but that's the current state of things. Low memory handling. So I mentioned in 2013 we split up the page queues. In addition to that, the page daemon, which is a kernel thread responsible for managing those queues and for reclaiming pages when necessary, is also split. So there's one page daemon per Numa domain per set of page queues. And the way that split was kind of done is such that all of the page daemons work more or less independently. They all have their own free page targets. They don't synchronize among each other very much. Pretty much the only case currently where they do that is for out of memory kills. All page daemons have to agree that their domains, their corresponding domains, are depleted of free pages before they'll actually issue an out of memory kill. So in doing some initial investigation after the Numa option was enabled in generic, one discovers pretty quickly that this kind of independent split doesn't work super well if you have the potential to wire most of your system's memory. So if you have a which basically removes it from the control of the page daemon. And so that happens when you have a really big arc, for instance. That problem is exacerbated when you have unbalanced Numa domains, because it's very easy to get into a situation where one domain is completely empty. The system has lots of free memory, though. From a global perspective, ZFS only ever looks at kind of global free page counts. So the page daemon responsible for the depleted domain kind of goes nuts, tries really hard to reclaim memory, but it can't do anything. So it ends up just consuming a ton of CPU. So that doesn't work super well at the moment. We have a few KPIs related to low memory handling in a sort of Numa-aware kernel. VM wait DOMs is a function which will put the calling thread to sleep until one of the specified domains has enough free pages according to some arbitrary threshold. So you can, if your thread is configured to only allocate from a subset of the system's domains, and none of them have enough free memory, you can go to sleep until at least one of them does. So you got pretty fine-grained control over how you wait for free pages to arrive. So the scalability improvements are kind of all over the place, and I'll just try to go through them very briefly. One of the more interesting ones is the use of a PID controller in the page daemon for the free page target. So very briefly, the way the page daemon used to work is it had a low watermark for free pages and a high watermark. Once the number of free pages crosses the low watermark, the page daemon wakes up and frees pages until we're back at the high watermark. That's simple and it works well for a lot of cases, but in practice what happens is you get this really bursty page daemon behavior. So as soon as that low watermark is hit, the page daemon suddenly has a ton of work to do, and it scans the queue, acquires lots of locks, consumes a lot of CPU, freeing pages, and then the system's at rest again. And as the free page count goes down, you eventually hit this burst again. So that didn't work well for certain FreeBSD users. What Jeff did was integrate what's called a PID controller. So rather than using a set of static watermarks, the page daemon looks at the dynamic properties of the current of the free page usage of the system. PID controller is basically a device which takes a few quantities as input. It looks at the current. It takes a look at the rate of free page consumption. It looks at the sort of instantaneous difference between the free page target and the number of free pages that are actually there. And it also has some notion of history of free page usage over time. So it has some sense of how quickly the system is running out of free memory, and it adjusts its target. It adjusts its target accordingly to try and meet that dynamic demand. So what that means is that if demand for free pages is relatively small and they're not being consumed at a high rate, the page daemon won't consume very much CPU in an attempt to meet that demand. It'll run more frequently than before, but it'll do less work each time. So its effect on the system is less bursty. The free page mutex, like I said, was global before. Jeff made it into a per domain mutex. Also added a per CPU cache, which can be used in certain situations, so you avoid a lock entirely when in the page allocation path. The free page mutex was actually used to synchronize a whole bunch of fairly unrelated things. It synchronized the physical memory allocator, but it also synchronized the system's reservation, the kernel's reservation system, which is basically used to try and attempt a super page promotion. It was also used to synchronize with the page daemon. So the page daemon would sleep on the free page mutex. So Jeff's work effectively split all of these use cases into separate synchronization protocols. Took a few atomic counters and made them into per CPU counters, or per domain counters at least. vwire count is a particularly good example. The system previously used an atomic integer to count the total number of wired pages, but that counter is written much more often than it's read. So in that case, it made sense to split it into a per CPU counter 9. Some of the work that I did was to try and alleviate the page queue lock contention by doing batching. So instead of acquiring the page queue lock in order to perform individual operations, requeue a page, dequeue a page, enqueue a page, we instead try to do that in a sort of batched, with a sort of batching mechanism where if you want to enqueue a page, you set some logical state in the page which declares your intent. You add an entry to a ring buffer, and you just go away. Once the ring buffer is full, the page queue lock is acquired, and all those logical operations are processed. So that ended up helping quite a bit. Other kind of miscellaneous things were to just break up the buffer cache into logical domains, like the actual terminology used in the buffer cache is domain, similar to Numa domains in the physical memory allocator, but there it's just a logical domain. Each domain is responsible for its own implementation of LRU, and it just eliminated or helped reduce the impact of some locking protocols used in the buffer cache. So what's next? And this is really just my idea of what I think would be useful and interesting to work on. So right now our Numa support is AMD64 only effectively. The SRAT parser, a lot of that code could be reused on ARM v8, which also, on ARM v8 systems which have an SRAT, although some modifications are needed. Power 9 systems can also be Numa. I don't know how Numa topology is actually encoded there, but there's some work to do to make sure that we actually detect the Numa topology on those systems. And there's some MD code changes that are needed, mostly in the bus DMA code for each platform, to make sure that we allocate DMA memory with Numa affinity. Currently, I would say the statistics collection for the Numa code is kind of lacking. There's no way to see the number of times in the history of a system's uptime, how many times the allocation policy failed to return a free page and we were forced to fall back to an alternate domain. So we have no visibility really into the effectiveness of the configured policies. There's some interfaces which we could implement. MSet domain, which I think Jeff already has a prototype for, does what I talked about earlier. You give it a virtual address range, and it sets a Numa allocation policy for that range. There's also libnuma, which is a library used on Linux that can be used by applications that want to request certain Numa allocation policies from the operating system. It kind of hides those details. It would be nice to have that on FreeBSD. There's a bunch of places in the kernel where we do static allocations, where again we can say a lot about the access patterns of those allocations, but we don't set things up so that memory references are local. So the per CPU region is one example of that, and it's actually somewhat tricky to address because per CPU, the PCPU region is initialized very early, in particular earlier than the SRAT parser runs, so that's going to take some work. The kernel thread stack allocator could probably use some rework. Again, there's cases where we're not using information that we have about kernel stack access patterns. There's the potential to plumb a notion of Numa policy or affinity through various other components of the system. We can define Numa allocation policies for jails, for instance. It could be nice to do something like that for mount points for file systems, where as the system administrator, you know a lot about what the access patterns of those of a particular file system is going to look like. ZFS integration is kind of still an open question. ZFS uses UMA to allocate most of the data buffers that it uses. Those buffers are, like I said, allocated from a kind of global round-robin policy. So there's not much, there's no real mechanism to plumb a ZFS-specific Numa policy at the moment. And I also hinted that there's problems with low memory handling in ZFS. The ARC reclaim logic consults a global counter of the system's free pages and then makes some decisions based on that. But it might be the case that certain domains are completely depleted while others have plenty of free pages. And so ZFS's response to what it considers to be a low memory situation might not be optimal, and it might not detect cases where specific domains are depleted. There's also a notion of Numa awareness and task queues. Task queues are kind of single thread, or I don't know how much I want to get into this. There's actually two fairly similar APIs, gtaskqueue and taskqueue. But we have no way of, or we have no easy mechanism to pin threads in a task queue, servicing a task queue to specific Numa domains, even when we know a lot about what their access patterns are going to look like. So I think there's some room there for better integration. There's a bunch of scalability work that we'd like to do. Right now, when you mlock some memory, that memory is counted as wired by the system. When ARC allocates some memory, that memory is counted as wired. They're both, mlocked memory is subject to system limits. So if you have a very large ARC, you actually can't use mlock, which is really silly. There's no real reason for that, other than the fact that we use this kind of shared mechanism to account for memory that's unevictable. So one of the things I want to do is kind of split that notion into two. And we have an array of locks that's used to synchronize updates to various parts of those page states. There's a lot of places or a lot of workloads where you see contention on those locks. And I think a lot of room to turn operations which are synchronized by those locks into operations which are synchronized on a per page basis instead. So operations on entirely independent pages don't result in contention because they hash to the same lock. And the last example I put on, when a Userland application faults and allocates a page, that page is immediately enqueued into the active queue. There's lots of situations where that page won't ever be seen by the page daemon because the process which allocated it exited shortly after that fault occurred. So you can imagine a scenario like a build. You have lots of short-lived processes which are doing tons of enqueues into the active queue from the page fault handler. But there's no real gain to be had from that because we don't care about LRU for those pages because they get freed immediately once the process exits. So we can definitely do better there. The page queue batching helps in that case, but it really doesn't eliminate the bottleneck. Page queue locks are still a major scalability impediment. And yeah, that's all I had. If anyone has any questions, Warner?
Okay, starting over, one of the areas I know that we need better integration is pushing domains and stuff down through geom as well. And that wasn't on your list.
Right.
So that there's disk awareness and bio awareness and so forth as well.
So yeah, that's a good example. To take a specific example, bios, which are used to basically encode I/O requests, and they're created at geom layer and sent to drivers, peripheral drivers, are allocated from UMA. Like I said, we use a global round-robin policy, but in situations where where the upper layers know exactly where that I/O request is going to go, it would make sense to request allocations from a specific domain. It is possible with UMA to request a first touch policy as well, but I suspect that that's not going to quite be enough because the bio zone, there's a single bio zone that's shared by all disks in the system, and the UMA kind of sits as this opaque block there. So anytime you allocate from UMA, it's kind of an open question which domain the resulting memory is going to be, which domain that the resulting memory has affinity for. I do believe that Jeff has some plans to kind of further plumb Numa through the caching layer of UMA. So UMA has a set of per CPU caches, and it has a global linked list of, again, of cached buckets of free items. And I know he'd like to make that into a per domain arrangement. That's not really trivial because of the way that UMA is actually used. So I don't know exactly what his plans are there, but I do think that's a known problem.
Yeah, the other thing we need to do with CAM is to do what we did with the network drivers and make all the SIMs that can support it multi-queue so that we can submit requests and have them complete in the same Numa domain as well.
Right.
So those were the two areas that I noticed weren't on the slides.
Yeah.
But nobody's working on them anyway, so I guess it doesn't matter whether they're on there or not.
Right. Yeah. I mean,
well, you could ask about them.
Sorry.
Thanks, Mark.
Yeah. Does anyone else have any questions? Does anyone using the new Numa-enabled generic have any insights into performance improvements that they've seen? Any problems that they've run into? I know a few users have reported regressions since Numa was enabled, and I've been working on patches to fix that. So while those issues are still open in head, they're going to be fixed in the next few days because most of the patches that I have been reviewed. But I'm wondering if there's any other sort of problem reports or shortcomings that people have encountered. No? Okay. Yeah, I guess that's it then. Didn't have anything else?